Hello, this talk is about region-optimized virtual coils. I have nothing to disclose. MRI often acquires unwanted signal. For example, in this brain image, we may only care about the occipital lobe and not care about anything from the rest of the brain. But if we use a small field of view, we are going to get major aliasing artifact. Similarly, here in the heart, we may only care about the heart, but we have to encode the rest of the slice to avoid the artifact. This is a problem because these unwanted signals require our experiment to be longer. So there are many current solutions to this problem, including hardware-based approaches and sequence-based approaches. This work, we use properties of MR receiver arrays to optimally suppress unwanted signal. Signal localization and suppression is done in case-based completely after acquisition. So our work is compatible with existing hardware sequence reconstruction method. Also, it enables free coil compression. So this leads us to our proposed approach that we call ROVir, short for region-optimized virtual coils. I will not go through all the details in this presentation, but all the details can be found in our recently published ISMRM paper. At a high level, the basic idea is that we have some calibration data with lava signal and interference ROI, and we are trying to create virtual coils as linear combinations of the original coils that maximize the signal to interference ratio. Interestingly, this optimization problem may look complicated, but it is converted into a well-known optimization problem known as a generalized Rayleigh quotient, which has a simple solution based on computing eigenvalues of very small matrices. So how well does this work? Here is our previous example of 32 channels of data where we are only interested in the brain. After going through the ROVir process, we can apply the weight we've obtained to new case-based data, resulting in 32 virtual channels of data. What you see from this example is that now we have a really clean separation of our signal from our interference. And we can simply throw out these extra coils that don't tell us about our region of interest. And this gives us a set of coils that focus on the brain, and it allows us to use a smaller field of view. And we still have multiple coils of case-based data, which allow us to do whatever kind of fancy reconstruction that we want, but with much less computational complexity because of the smaller number of channels. And for those of you who remember the pills technique, this is basically an optimal way of forming virtual highly localized coils from a set of non-localized coil sensitivities. And these are application examples of ROVir. We can apply ROVir to reduce the field of imaging to suppress the artifact, and we can do our volume suppression with ROVir. One of the nice features of this method is that we have a lot of flexibilities to start the beam to look at the ROIs that we want. For example, this movie was created all from the same case-based data, just choosing different regions to care about. And another nice feature is that we have complete quantitative control over the balance between retained signal and interference. You can choose ROVir coils with the amount of signal and interference that you want. In conclusion, ROVir is a beamforming approach for optimal signal localization and suppression. It is simple to compute, it is optimal, and it has broad compatibility with hardware sequence and reconstruction. We are also excited to share that we've recently combined ROVir with SMS to achieve a single breath-hold scene imaging. You can see details in this other talk. Thank you for watching this video.